Welcome back to Basic Electronics. In this lecture, we will look at a very useful theorem called the Thevenin's theorem. We will first try to understand why it is possible to represent a circuit with its Thevenin equivalent form. We will then look at how to extract the associated parameters, namely the Thevenin resistance and the Thevenin voltage. After that, we will consider a couple of examples to illustrate how a circuit can be represented by its Thevenin equivalent. We will also see how the Thevenin parameters can be extracted graphically. So let us get started. Thevenin's theorem is a very useful and important theorem, and particularly in electronic circuits, we will find it very useful. But before we look at the statement of the Thevenin's theorem, let us see briefly where it comes from, and we will do that with the help of this example. Here is a circuit to which we have connected a load resistor RL, and we are interested in this voltage across RL. And in particular, we want to ask this question: how is V related to the circuit parameters? We begin by assigning node voltages to these various nodes in the circuit with respect to a reference node. So let us first choose a reference node. We have taken that as the reference node. So the node voltage there is 0 volts. And with respect to that reference node, this voltage at node A is V1, the node voltage at B is V2, and the voltage at node C is V3. Now what we will do is write KCL equations in terms of V1, V2 and V3 at these nodes A, B and C. And in doing that, let us define G1, a conductance, as 1 over R1, G2 equal to 1 over R2, etc. These are our KCL equations. Let us look at KCL at node A. That is our node A. We have three currents entering or leaving node A. There is one current going like that, and that is V1 minus V3 divided by R1. So that is G1 times V1 minus V3. And since that current is leaving this node, we will take it as positive. Then we have this current V1 minus V2 divided by R2. That means G2 times V1 minus V2. And then we have this current I0 entering the node. Since this current is entering the node, we take that as negative, and that's why it appears as minus I0 in this equation. And all these currents must add up to 0, and that gives us KCL at node A. In a similar manner, we can write KCL at node B and KCL at node C in terms of the node voltages V1, V2 and V3. And we can now write these equations in a matrix form like that. Let us look at one of these equations. Let's say the first one. This first equation comes from KCL at node A, and let us verify that. What is the coefficient of V1 in this equation? It is G1 plus G2, so that goes over there. That's going to multiply V1. What about V2? The coefficient is minus G2, so that goes there, and that multiplies V2. And the coefficient of V3 is minus G1, so that goes over there. In addition, we have minus I0 over here, and since that does not depend on V1, V2 or V3, we take that to the right hand side, so it becomes plus I0, and that is how it appears here. So this matrix equation is of the form G times V equal to Is, where G is this matrix here, 3 by 3. V is this column vector consisting of V1, V2, V3, the node voltages in our circuit, and Is is the source current vector, this one. Alright, now if you recall, our objective is to find a relationship between V and the rest of the circuit, and in order to do that, we want to solve this matrix equation, and obtain V2, since V2 is the same as V here, because this node voltage is 0. And V2 can be obtained using Cramer's rule. And what does Cramer's rule say? It says that V2 is given by D1 divided by D2, where D1 is the determinant of this matrix with the second column replaced with this RHS vector, and D2 is the determinant of this matrix as it is. So let us do that and simplify things after that. Okay, so this is what we have for V2, the ratio of two determinants, determinant of this original G matrix with the second column replaced with the RHS vector like we mentioned in the last slide, and the determinant of the G matrix itself. All right, now let us denote this determinant by delta 1, and what we should note about delta 1 is that it does not have RL or GL in it, so its value is independent of the load resistance value. Let us look at the denominator now, that is determinant of G. This is our G matrix, and this determinant does depend on GL. We have GL over here, and what we will do now is write this column as the sum of two columns, column 1 minus G2, G2 0, column 2 0, GL 0. And if we do that, we can write this determinant as the sum of two determinants. This determinant has no GL term in it, whereas this one does have GL in it right there. Let us denote this first determinant by delta, and let us write this second determinant as GL times delta 2, where delta 2 is the determinant of this matrix here. And notice that we don't have GL here anymore because that has been taken outside. All right. So with these substitutions, we can write V2 as delta 1 divided by determinant of G, that is delta 1 divided by delta plus GL delta 2, that term, where delta, delta 1, delta 2 are all independent of GL. So the only dependence of V2 on GL is right there. So here is V2, once again delta 1 divided by delta plus GL times delta 2, and let us emphasize once again that delta 1, delta and delta 2 have no dependence on GL or RL, and they will only depend on the circuit parameters here. All right, let us now look at the open circuit value of V2, that means the value of V2 when RL is infinite. And when RL is infinite, GL, which is 1 over RL, becomes 0, and therefore we have V2 equal to delta 1 divided by delta. So that is our V2 in the open circuit condition. We can now rewrite V2 by dividing both the numerator and denominator by delta. So in the numerator we get delta 1 divided by delta. In the denominator we get 1 here. So 1 plus GL times delta 2 over delta. Now delta 1 by delta is nothing but V2 OC, V2 open circuit. So we replace that with V2 OC, and that gets divided by 1 plus delta 2 over RL times delta. Here we have used the fact that GL is 1 over RL. And now let us multiply both numerator and denominator by RL to get RL divided by RL plus delta 2 over delta times V2 OC. Now it turns out that this quantity delta 2 divided by delta has units of resistance, and you should really go back one slide and check that out. So let us define R Thevenin, that is Thevenin resistance, as delta 2 divided by delta, and with that we get V2 equal to RL divided by RL plus R Thevenin times V2 OC, like that. Oh, the stop sign has come, and why is it there? That means there is some unfinished business, and that is this delta 2 by delta. You need to really go back and check that it has units of resistance. So do that, stop the video here, and when you complete this assignment, start again with the video. So this is our expression for V2, and it is looking very much like voltage division formula. If we have a source which is equal to V2 OC, like that, and R Thevenin and RL in series, then the voltage across RL, which is V2 here, would be RL divided by RL plus RTH times VTH. So this circuit and this expression are compatible with each other if we have VTH equal to V2 open circuit. In other words, this expression allows us to replace the original circuit with an equivalent simpler circuit, and that simpler circuit is the Thevenin equivalent circuit. So here is our original circuit, and this entire circuit can now be replaced with this much simpler circuit consisting of only one voltage source in series with one resistance. The voltage is called VTH or Thevenin voltage, and the resistance is called R Thevenin or RTH. And later, of course, we will look at how we can obtain VTH and RTH from the original network. And that brings us to Thevenin's theorem. If we have a circuit consisting of resistors, independent voltage sources, independent current sources, and dependent sources such as current controlled voltage source, current controlled current source, etc., then Thevenin's theorem says that this circuit can be represented by its Thevenin equivalent circuit consisting of a voltage source VTH in series with a resistance RTH. And now imagine that we have a load resistance RL connected between A and B to the original circuit as well as to the Thevenin equivalent circuit. Then Thevenin's theorem says that the load resistance does not see any difference between the original circuit and its Thevenin equivalent. That means the voltage across the load resistance or the current through the load resistance would be identical in these two cases. Alright, now the next question that comes up is how do we figure out VTH and RTH from the original network? So let us look at that. First, let us look at how to get VTH from the original circuit. Since the two circuits are equivalent, the open circuit voltage must be the same in both cases. Now let VOC be the open circuit voltage for the left circuit here. That means we don't connect anything between A and B and measure this voltage VOC between A and B. For the Thevenin equivalent circuit, what is the open circuit voltage? If we don't connect anything between A and B, there is no current, and therefore there is no voltage drop across RTH, and therefore this open circuit voltage would be the same as this VTH. And therefore we conclude that this VTH is the same as the open circuit voltage seen between A and B in the original circuit, and that is what this equation tells us. What about RTH, the Thevenin resistance here? That can be found by different methods, and let us see what those methods are. Method 1, here is our original circuit and that is the Thevenin equivalent representation. What we do is deactivate all independent sources in the original circuit, and we do the same thing in the Thevenin equivalent circuit as well. And in the Thevenin equivalent circuit, the only independent source is this voltage source here, and when we deactivate that, we replace that with a short circuit like that. And what we see then between A and B is simply the Thevenin resistance RTH. And now if we look into the port AB of the original circuit with the voltage sources and current sources deactivated, then whatever resistance we see must be the same as RTH. Often RTH can be found by inspection of the original circuit with the independent voltage sources and independent current sources deactivated. And if that does not work, what we can do is to use a test source. We can use either a test voltage source like that, or we can use a test current source like this. And what we do then is, for example, if we use a voltage source, then we find this current Is, and then RTH is given by Vs divided by Is. In this case, where we have a test current source, then we find this voltage drop between A and B, and then RTH is given by Vs by Is. Let us look at our second method now. This is our original circuit, and that is the Thevenin equivalent. We look at two things. One, the open circuit voltage between A and B in both cases. Second, the short circuit current which flows from A to B when A and B are shorted, and we do that again in both cases. And because the original circuit is equivalent to this Thevenin representation, VOC here must be the same, and similarly IAC here and IAC here must be the same. So we use this fact to obtain RTH for the Thevenin representation. Let us see how. Let us look at this circuit. The open circuit voltage between A and B is the same as VTH here, because there is no voltage drop across RTH, the current being 0, and therefore we get VOC equal to VTH, this equation here. Alright, let us now look at the short circuit current. ISC is simply VTH divided by RTH, because there is no other resistance in the circuit. So that gives us ISC equal to VTH divided by RTH. And VTH is the same as VOC, therefore ISC is equal to VOC divided by RTH. And that gives us a formula to obtain RTH, that is RTH equal to VOC divided by ISC. Now since this VOC and this VOC are identical, because the two circuits are equivalent, and also because this ISC and this ISC are the same, what we can do is, in the original circuit we find the open circuit voltage and the short circuit current, and then RTH is given by that open circuit voltage divided by the short circuit current. And note here that we do not deactivate any sources in this case. So the independent sources are left as they are in the original circuit. Let us find the Thevenin equivalent of this circuit here as seen from RL. So we need to find VTH and RTH. Let us find VTH first. And how do we do that? VTH is the same as VOC, the open circuit voltage between A and B. So we remove RL and then find this voltage, and that is the same as VTH. That is a straightforward calculation. There is no current through this 2 ohms resistance, so no voltage drop there, and therefore VOC is the same as this voltage drop, and that can be found by voltage division. That is 3 ohms divided by 9 ohms times 9 volts. So that comes to 3 volts. So our VTH, which is the same as VOC, is 3 volts. Next, let us find RTH. And how do we do that? In the original circuit, we deactivate the independent sources. In this case, there is only one independent source, that's a voltage source. So we short it, and then we look from this port AB. And this is what we see from AB. This 6 ohms and 3 ohms come in parallel, and that combination comes in series with these 2 ohms. And therefore our RTH turns out to be 3 parallel 6 plus 2 or 4 ohms. So our Thevenin equivalent circuit has VTH equal to 3 volts and RTH equal to 4 ohms. Another example. This is a little more complicated than the previous example. We have two independent sources now, a current source 6 amperes and a voltage source 48 volts. And we want to find the Thevenin equivalent circuit as seen from AB. Let us look at RTH first. How do we find RTH? We deactivate the independent sources, that is this current source and this voltage source. The current source is replaced with an open circuit and the voltage source is replaced with a short circuit. And now we look from AB and find the resistance. That resistance is our RTH. And that is fairly straightforward to do. This 4 ohms and 2 ohms are in series, so therefore we have 6 ohms, and that combination comes in parallel with 12 ohms, and that entire combination is 4 ohms. On this side we have 4 ohms in parallel with 12 ohms, and that turns out to be 3 ohms. So altogether between A and B we have 4 ohms plus 3 ohms or 7 ohms, and that is our R Thevenin. Let us now look at V Thevenin. V Thevenin is the same as VOC, this voltage here. And how do we go about finding that voltage drop? We note that this current I must be 0 because there is no return path for this current. There is an open circuit here, and if this current were not 0, then that would lead to violation of the charge conservation principle. Alright, once we figure that out, the rest of the calculation is straightforward. What we do now is find this voltage drop between A and C, this voltage drop between C and B, and then VAB is simply VAC plus VCB. So let us do that. Since this current is 0, we have two independent circuits here. One circuit is here and the other circuit is here, and that makes things very easy. Alright, let us look at VAC first. What is this resistance? As we have already found out, that is 4 ohms, and therefore 6 amperes going through 4 ohms gives us 24 volts. So that is VAC. What about VCB? VCB is given by voltage division of this 48 volts between 12 ohms and 4 ohms. So it would be 12 divided by 16 times 48, and that turns out to be 36 volts. So altogether between A and B we have 24 volts plus 36 volts, and that comes to 60 volts. So that is our open circuit voltage, and that is the same as VTH. So we have VTH equal to 60 volts, RTH equal to 7 ohms, and our Thevenin equivalent circuit therefore looks like this. Let us now look at a graphical method for finding VTH and RTH. This is a Thevenin equivalent circuit of some original circuit, and what we do is connect a voltage source here and plot this current as a function of this voltage, and the plot that we are going to get is shown over here, and let us now try to understand why the plot looks like this. What is this current? It is VTH minus V divided by RTH, this equation, and note that it has a negative slope. The slope is minus 1 over RTH, and that has reflected in this plot here. What about the intercept of this line on the V axis? To find that, we put I equal to 0 and we get V equal to VTH. So that gives us the X intercept, and VTH, remember, is the same as VOC. What about the Y intercept? To find that, what we do is put V equal to 0. That gives us I equal to VTH divided by RTH, this quantity here. And if you recall, that is the same as the short circuit current. That means it is the current that would flow if we connect these two nodes by a wire, just a short circuit. Alright. So now from a plot like this, we immediately find VTH as the intercept on the V axis, and ISC, which is equal to VTH by RTH, as the intercept on the I axis. And from these two numbers, we can find our Thevenin voltage and Thevenin resistance. And as a remark, let us mention that instead of a voltage source here, we could have also connected a load resistor, say R, varied that resistance, and then plotted I versus V again. We would get the same plot once again. Let us apply the graphical method that we just discussed for this circuit, which we have already considered earlier. And here is the SQL circuit file, so you can run this simulation and obtain the plot that we are going to look at very soon. Okay, so how do we go about it? We connect a voltage source between A and B like that, and then plot this current as a function of this voltage. And when we do that, VOC is given by the intercept on the V axis, and ISC, the short circuit current, is given by the intercept on the I, or the current axis. And here is the result, I as a function of V. The intercept on the V axis is 60 volts, and that gives us VOC, and the intercept on the current axis is 8.57 amperes, and that gives us ISC. And VTH is the same as VOC, 60 volts, and RTH is the same as VOC divided by ISC, and that turns out to be 60 divided by 8.57 or 7 ohms. And these numbers, of course, are the same as what we got earlier when we analyzed this circuit using different methods. To summarize, we have become familiar with Thevenin's theorem. We have also seen how to represent a given circuit with this Thevenin equivalent form. This background will be useful to understand RC circuits, amplifiers, etc. That is all for now. See you next time.